Hello everyone, I am Dr. Shruti Pandey from University of Louisville and we are taking this topic capacitors today. So let's briefly discuss about capacitors. So as we have already discussed in the class the basics of capacitor. So if we have a voltage source, right? If we have a voltage source, let's call it as 24 volt source. And if we have a capacitor connected to it, so this is positive negative of voltage source, and capacitors are initially, so the first step is initially capacitors are always, or initially the plates of capacitors are always electrically neutral. Right, so by electrically neutral I mean that the capacitor plates, like if there are 3 positive charges, there are 3 negative charges also, and similarly in this plate if there are 3 negative charges, there are 3 positive charges also. And what happens, like this is the first step, that initially these capacitor plates are electrically neutral. That means number of positive ions is equal to number of negative ions. The second step is positive terminal of voltage supply attracts negative ions from upper plate of capacitor, right? So one by one, first this will be attracted here, so only one positive is left. One positive is alone now, like negative is detached. So the second negative is also attracted. Now this positive is also free. Then this is also attracted. Now this positive is also free. So that way, and similarly, because the like charges, we all know this, that like charges do not attract each other, rather unlike charges attract each other. So all the negative from the upper plate of the capacitor is attracted by this positive of the supply. Similarly, all the positive is attracted by the negative of the supply, and here at the lower plate of the capacitor, the left ones are only the negative charges. Similarly, the left ones at the upper plate of the capacitor are positive charges. So now we have positive accumulated over the upper plate and negative accumulated over the lower plate, and that way we, like, this is the process of charging of a capacitor, and this keeps on going until this capacitor attains this supply voltage, right? Until it attains 24 volt, because these two are connected in parallel. So the current is going on, the conduction is going on and going on until this capacitor attains or is equal to V input voltage. Okay, so third step is like all the process will keep on going until VC is equal to V in, where VC is this voltage and V input is this voltage, that is supply voltage. Okay, so that's the first thing. Now what is the one more thing I would like to tell you, which also probably we have discussed. So how are these positive and negative charges intact over the upper and lower plate? What happens is, like, you know that in the capacitor this part is dielectric, right? So this part is dielectric. And what is dielectric? Dielectric is kind of insulator, right? And insulator, that means that this dielectric is not allowing this positive charge or any of the charge to travel from here to here, because there is a dielectric in between, or insulator is there in between, which is not allowing the penetration of the charges, right, through it. Okay, so what happens inside the dielectric? First of all, you can see that there are positive at the upper, negative at the lower. Therefore an electric field is, an external electric field is generated, because current flows from positive to negative. So we say that an electric field is generated here, which is an external electric field because of these charges, right? What is all going on in between the dielectric? So there are lot of positive negative ions, positive negative, I mean like this. They are roaming here and there until no charges, until no charge is there accumulated here, or no prominent charge of accumulation is there at the lower plate. Until that, the ions which are there in the dielectric are just roaming here and there like this randomly, right? But when there is accumulation of positive charge and negative charge, how is the orientation inside the dielectric? Like these are positive, these are negative. The orientation is like this. They all are oriented in this manner, right? Because from all of these, the negative ones are at the upper side because they are positive here. So these positive are attracting the negative ones. These positive are attracting these negative ones. Similarly, in the downside, here are plus, 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 right? Because these positive are being attracted by these negative. Okay, so that's the internal or the in-between orientation of charges within the dielectric. So an external dielectric, because if this is positive, this is negative, so an external electric field is formed in this manner, that is downward. And you can see an external electric field also, like this is, you can see that this all is positive accumulated here and this all is negative accumulated here. So there is an internal electric field from this positive to this negative, right? So that is in reverse direction. So external dielectric field, because of the polarities or the accumulation of charges over the upper and lower plate. So this is that direction and this is the lower direction. What is this electric field? This electric field formula is E is equal to V by D, where V is the external voltage supply and D is the distance between them, right? So this is supply voltage and this is distance between them, right? So this is your first formula, remember this. Okay, the second formula is that what is the capacity of this capacitor, like how much capacity it has to accumulate the charges, right? So that capacity C is equal to Q by V, where Q is charge and this V is again supply voltage, right? And this is ability of capacitor to store charge, right? So this is your next formula. This is formula number 1, this is formula number 2. So the question I have given you in assignments is based on this formula, okay? Probably I have asked how much is the charge stored in the capacitor or over the plates of the capacitor. Okay, so these are the two formulas, and then there are 3-4 other formulas which I would like to go through. So just a second. Yeah, so there are few other things which I would like to tell, that Q is equal to C into V, that is, this is that how much charges are accumulated. So that Q is equal to capacitor, like, so I'll tell you in the downside I have taken one example also. I'm going to discuss that. Meanwhile, C is the capacitance and has the unit of farad. So this capacitor has the unit farad. Do remember this. Farad is a very large amount of capacitance, right? Like 1 farad is very huge, and generally the capacitors are rated in this micro unit. So this is 10 to the power minus 6, that is microfarad. So usually you will see this microfarad rating, right? Not 1 farad or 2 farad, rather this microfarad is the more general one. So yeah, this is a capacitance formula. So you know that Q is equal to C into V multiplied by V. So capacitors are rated by capacitance and voltage rating. So whenever you are going to buy a capacitor, I have shown you a photograph also of a capacitor which had 2 legs. So you saw that this capacitor had 2 ratings written over it. One was the one which I circulated in class. So I think it was 250 microfarad was the capacitance rating, and 250 or 200 volt was the voltage rating, right? So these are the 2 ratings which are mentioned over the capacitor. Okay, so For example, a capacitor may be rated at 25 microfarad and 80 volt. So this is also a general rating of a capacitor. And if somebody is asking you, or the question has been asked, that what is the charge stored in these capacitor, so it will be, in this case, like in this example, it will be 25 10 raised to the power minus 6 multiplied by 80, right? So that is the value of capacitor here. Okay, so yeah, this was a thing. Then next thing is that how do we represent a polarized capacitor? So I told you that there are two kind of capacitor. One is non-polarized one is this kind of polarized one. So the non-polarized one do not have any positive negative written over it. Like you can connect the positive and negative of supply anywhere in these or to the any leg of this capacitor. But the polarized one do have this positive and negative. Like this is a non-polarized, it do not have, it has only two plates, and the polarized one has positive and negative written over it, right? So this is a symbol of a polarized capacitor. So now this is very important. What is the current flowing across this capacitor? So I is equal to C dV by dt. So dV by dt, you know, like this is connected to the voltage supply, and this capacitor has attained that entire voltage supply which was here after being charged. So the current is equal to C, that is this capacitance, multiplied by dV by dt. That means the rate of change of voltage, right? So this voltage, like this is maybe let's take an AC voltage here, right? Let's take an AC voltage here. By AC voltage I mean that this is time, this is voltage, and voltage is changing with time, right? So the change in voltage with respect to time is this. Okay, so that is I is equal to C dV by dt. Then the Vt formula is like from here, if you are going to integrate all of these, so I integral and this integral, so this formula, this Vt formula has been derived from this formula itself. So if you are going to integrate both the sides, so Vt will be 1 by C, right? You know this, right? 1 by C I is equal to dV by dt. And now if you are going to integrate both the sides, it will be Vt is equal to this 1 by C is constant, it will come out, and it will be I dt plus K, right? So this formula is derived from this one. So that's C. So for the first formula was E is equal to V by D. The second formula was Q is equal to CV. This is the third important formula, I is equal to C dV by dt. And from this third important, this is the fourth important formula, that Vt is equal to 1 by C I dt plus K. So these are the four formula you need to remember. And there's one more last formula, which is this. Capacitance is equal to epsilon A by D, where epsilon is a constant. So you can see that this is capacitor. So this is one plate of the capacitor. The downside is the other plate. So this is the next other plate of the capacitor. Or maybe you can write like, or you can see like this. So this plate might have, this is the upper plate. So it might have, and this is the voltage supply, right? So the upper plate has accumulation of positive charges. The lower plate has accumulation of negative charges. So the capacitance of this capacitor is equal to epsilon A. A is the area of this plate, right? You can see the area of the upper and lower plate is same. So area of the plate is A, and D is again the distance between the positive and negative plate. Then this epsilon can be broken down into epsilon R multiplied by epsilon naught, where epsilon naught is always constant, and epsilon R can be varied as per this. So these are the epsilon R values. For air, the epsilon R will be 1. For diamond, it will be 5.5. So you know this, like this dielectric which is there in between these two plates is an insulator. So these are all these insulator. ER is relative permittivity, right? So this is relative permittivity. So these are the constant values for this permittivity. So yeah, that's it. And probably if I'm going to give you any question regarding this formula, then I will definitely give you ER value, and I will also mention this E naught value in the paper. Okay, so you need to only remember this formula. So in capacitance, by now, how many formulas did you remember? You need to remember, this is first, this is second, third, fourth, and this is fifth, right? So these are the 5 formulas. The next thing which is also important here is that how do we calculate the equivalent capacitance of a circuit, right? So you can see that here C1, C2 and C3, these all 3 capacitances are connected in series, right? You can see that all 3 will have the same current in it. So these capacitances are connected in series. So what's the formula? So you know this, that if 3 resistances are connected in series, this is R1, this is R2 and this is R3, and somebody is asking you the R equivalent, you know that in case of series it is R1 plus R2 plus R3, and in case of parallel it is 1 by R1 plus 1 by R2 plus 1 by R3 is 1 upon R equivalent, and R equivalent will be R1, R2, R3 upon R1 plus R2 plus R3. So that's the case in series and parallel. When we are considering or when we are talking about resistors, exact reverse or opposite case is there in capacitor. So when capacitors are connected in parallel, the formula is C1 plus C2 plus C3, and when these 3 are connected in series, it is 1 upon C1 plus 1 upon C2 plus 1 upon C3, same as this, and this will be same as this, right? So yeah, so that was it. That I mean, this is these are the formulas or things or concepts you need to remember. One very important factor or a statement you need to remember is that capacitance or capacitors does not allow sudden change in voltage, right? So we have already discussed about it, that these are the voltage sources and this is a capacitance, plus plus plus, minus minus minus, it also has minus into it. So whenever this positive is attracting, it is attracting one charge at a time, right? Or you can say, or I mean, I'm telling you just this thing just to correlate it, or you can remember it in this way. But the point is that if this is 24 and if I want a capacitor, right, this is time and this is a voltage, right, and this is across capacitor. If I want capacitor at 2 seconds, t is equal to 2 seconds, if I want capacitor to get charge immediately at 24 volt at this second or 2th second, then it cannot charge like this, right? So if this is 24, so I want that at 2 seconds the capacitor, this VC, capacitor voltage, should be 24. So this is not possible. Rather, at 2 seconds, at time t is equals to 2 seconds, this will start building, right? So this is VC, this will start building, and at some point of time it is going to achieve this 24 volt, right? So this is the total time of charging. Similarly, if I want to discharge this capacitor, right, so you know it that if you want to discharge this capacitor, you can connect a bulb into in parallel to it. This bulb is a resistive load, and resistive load has the capability, it is a dissipating element, it can eat any power you give to it, right? So this is plus 24 and this is minus. So earlier the capacitor was getting charged like this, right? Current flows from positive terminal of the battery to negative, or positive of V input to negative. So earlier the current was flowing like this, right? So earlier the current was flowing like this while charging, right? So while charging, you can see that the current direction, this was positive, this was negative, the current direction was like this. But in the discharging, what is happening, like when now this is complete 24 volt, and now let's say I disconnect this, I say that I disconnect this voltage source from the capacitor. Now capacitor is going to work as its individual or as an isolated or independent voltage source, and it is going to light this bulb via this way, via this route. So current goes from positive of the terminal or positive of this to this resistor, and then it is going to come back to this negative, right? This way. Okay, so now you can see that the current direction is reversed. So in case of discharging, the current direction is reversed. So anyhow, as I have written the statement that capacitor does not allow sudden change in voltage. So if I'm trying to charge it, right? So if I'm trying to charge it, current is in this direction and capacitor is not allowing change in voltage. So what will then change? Then the change will be in current, and that is what it is reflected here, that the current direction has changed because the voltage is still the same. This was also plus minus, this is also plus minus. So voltage polarity is not changing, rather current is changing. So first thing you need to remember this. Second thing you need to remember this, that in the process of discharging, the current direction is changing. And third thing you need to remember is that the rise in current, the rise in voltage is slowly or exponentially. It is not instantaneously. So maybe I can write here that capacitor does not allow sudden change, or you can also write instantaneous change. Right? So, and above all this, like we have also discussed several application of capacitors, in which one application was this. I told you that this is a rectifier and this is right. So this is V input, which is like this. This is voltage, this is time, and this is V output, or maybe I can write V, or maybe I can reverse these things. I can connect capacitor first and then this. So here it is V output plus minus, and this is VC, and this is a rectifier circuit. Rectifier is something, this is an application of capacitor, right? So rectifier is something which converts AC supply into DC power. So let's say that this is a rectifier or a charger, like all the chargers, mobile chargers, battery laptop chargers, all of these has rectifier into it. So it is taking AC input supply from the plug, from the main supply which we are getting in our houses, and after this we need to connect a telephone battery, right? Because it requires DC power. So here the output is DC, input is AC, and therefore it is a rectifier circuit. So if this capacitor filter would not be there, we will get this kind of DC, right? So this is time, this is voltage, we would get this kind of DC, and this is a pulsating DC. So obviously this is DC because it do not have any negative component into it. So it is DC, but if we want somehow pure DC, right? Not exactly pure, but somehow like better DC than this, then we can use capacitor. Because what will happen here, like what is happening here, like this is input, and let's call it as 24 sine omega t. So that is V input, and this is 24, right? So this is a waveform which is 24 sine omega t. This is V input, this is T, right? And similarly here also. So until this point, that is 24 volt. Until this point, this terminal is giving 24 volt, and from this terminal it is coming 0 because initially capacitor was discharged. So this part of diode is getting plus 24, this part is getting 0. That means it is forward bias or conducting. And if it is conducting, current will easily flow like this, right? Current will easily flow like this, and capacitor will charge itself slowly, right? So if this is V output, we are getting slowly, we are getting over that 24 volt, right? So let's call it as that this was 24 volt. What will happen after that, or after the capacitor is fully charged? After the capacitor is fully charged, so now this is plus minus 24 volt, right? So now what will happen, that the negative terminal of the diode will get this 24 volt plus 24 volt, and this part, like after this part, after this, in this entire part we are getting input voltage less than 24, like this was 24 volt, or maybe we can see from this waveform that after this or after this, this is 23, this is 22, 20, 21, whatever. So in this entire path, the voltage value is less than 24, right? Because this is also minus 24, this value is also minus 23. So everything in this green is less than 24, and this is V input. So at this part it is less than 24 and this part is 24. So that means that this is at higher potential and this is at lower potential. So that means that diode is open circuit now, and there will be no conduction of current via this. Okay, so now capacitor is fully charged. It is looking for somebody to take its charge, or it wants to get discharged, but there is no connection between supply, input supply and capacitor, because capacitor is like this right now. Capacitor is open circuit like this, right? Open circuit like this. So where is that capacitor, or from where this capacitor is going to get its path? The capacitor will get its path like this, because current flows from positive terminal to negative. So now capacitor will discharge all its energy via this resistor R, right? So now till this point we are going to get this kind of discharging current, like capacitor is trying to discharge. So this is charging and this entire part is discharging, right? So this is how. And now if I want like some more, I mean a better waveform, like something like this. So what am I going to do? If I will increase the capacity of this capacitor, by that I mean that initially the capacitor is 20 microfarad. Let's say that I have increased the capacity to 200 microfarad, right? So 200 microfarad capacitor will take lot more time to discharge when we compare it to 20 microfarad. So if the 20 microfarad waveform is something like this, the 200, this is for 20 microfarad. The 200 microfarad waveform will be something like this, right? And here let's say that again the diode becomes forward bias, and there again the conduction starts, and there again the capacitor is trying to charge. So there will be again a charging, right? So again there will be charging and then discharging, then again charging. So this is more, or I mean this looks better DC waveform, right? This is a better DC waveform when compared to this. Okay, so briefly, this was a reason, or this was an application, that how capacitor is helping in smoothing the waveform, or the smoothing of the DC waveform coming at the output of this rectifier circuit. Okay, so that was all with respect to a very brief introduction or brief about capacitance. Okay, thank you.